Yes, so welcome back to the second lecture of today. And those who could not join yesterday for any reason, I like to inform them. So today the lecture will be delivered by Professor S.A. Katre, who is a chair professor, Lokmanya Tilak chair professor at Savitri Bai Phule Pune University, Pune, and he retired as a professor and head from Department of Mathematics, Savitri Bai Phule Pune University, Pune. And yesterday he started his series of lectures on ancient Indian mathematics, and he is targeting the topics Kutakka method, Thales equation, and search. So yesterday he talked about Kutakka method, and he will continue from where he stopped yesterday. So I welcome you, sir, and please start your session.
Yeah. Yes. So you have heard very nice lectures so far. Lecture by Professor Dani on geometry was very interesting. Many things from Shravana Sutra he had discussed. Then lectures by Dr. Smita Bedekar on Lilavati. So you have understood what type of arithmetic was done by Bhaskaracharya. And then some important topics from arithmetic and algebra we are discussing. So in my previous lecture, I discussed Kuttaka method, which is a very important method, and I have told how that is still useful. For example, it can be used in the RSA cryptography calculations because there is an algorithm which is given to solve a linear dependent equation in two variables, and solving it is equivalent to solving tiny remainder theorem in some sense. So that's why it is useful in many applications and a very important way of writing the solution using an algorithm. So these methods were algorithmic. These ancient Indian mathematicians, they used to somehow get the result and uh, write it in an algorithmic form. So if you do it step by step, you will arrive at the answer. That's the idea. So now we are looking at the next topic, that is Pell's equation. This Pell's equation is now called Bhaskaracharya equation or Brahmagupta Bhaskara equation. So we shall see what this equation is. I would also like to mention two books as was requested by participants and mentioned by Professor Gauri Shankar. So there is one book in English, Bhaskaracharya's Bijganit, and its English translation. So it does not have explanation. Maybe at one or two places it has explanation, but the translation of the original verses in Bijganit is given here. And this book is published by Bhaskaracharya Pratishthan. and it is written by S.K. Abhyankar. So those who knows Professor Sriram Shankar Abhyankar, who founded the Bhaskaracharya Pratishthan, and he is a very well-known algebraic geometer. He has done great contributions to this topic of algebraic geometry, and then his father was also a mathematician. He was a mathematics professor, and he has translated Bhaskaracharya's Bijganit in a very nice way. And Aryabhata's Ganita Pada. Pada means one fourth, in the sense that Aryabhata's Aryabhatiya, that is the book, which has four parts, and the second part is Ganita Pada. And Ganita Pada and its Marathi translation, unfortunately, Professor S.K. Abhyankar did not do the English translation, but the Marathi translation is there. Those who know Marathi, they can understand this thing. However, as I see, there are many books in Hindi and English also on these, because they are very classic books. Ganitpada as well as Bij Ganit, they are very classic books, and various Hindi and English translations are available, and you can also find these on from the internet, and many of them are downloadable also. So it is good to search internet and see the translations of these. Although the original books are in Sanskrit, the translations are there and explanations are also there. Many times in many books, the problems are also solved using these the translations. So also on the internet, if you go to Wikipedia, you will get some information about the various problems that have been discussed. That is, if you try Pell's equation, then you will also get information about the work of Bhaskaracharya there. So last time I specifically discussed the method of Aryabhata for solving the Kuttaka related problems. So today we shall see Pell's equation as done by Bhaskaracharya, because at the time of Aryabhata it was not known how to solve it, but Brahmagupta started solving equations of this type. And then Jaidev contributed more to it, and Bhaskaracharya gave the final touch, and so it is called Brahmagupta Jaidev Bhaskara equation. And this equation, it was termed as Pell's equation by Euler earlier, and it was solved by these Indian mathematicians, mainly Brahmagupta, Jaidev, and Bhaskara. This equation is a quadratic equation. So usually what happens in mathematics, you go from simpler to more complicated. So Kuttaka equation that we considered there is ax plus b equal to cy plus d. So you know that it is a equation in two variables, of which you want to solve it and get integer solutions, that we studied last time. It is an equation of degree 1. X and y, these are the variables, and degrees are 1. So once you are able to solve such an equation in integers, of course at that time fractions were not known. After fractions, more difficult complicated numbers were not known, uh, are not studied, although some idea was there to people. So you want to solve equations with integer solutions or rational solutions, such were the problems considered. And therefore the next problem, x square minus dy square equal to 1, this is the equation that you want to solve. This is a second degree equation, note. And how to solve? Of course, second degree equation can be more complicated also, like x square plus 2xy or 7xy plus something into y square equal to some constant, or there can be again linear terms. So again cx plus dy and so on, such terms may appear. So this becomes more complicated, and at least we should try to solve equations which look simple at the beginning. Sometimes more complicated equations are reduced to this equation, and then one can solve it. And you will see why this x square plus dy square equal to 1, why it is not considered. Because you want integer solutions. If you put plus sign here and d is some positive integer, then uh, suppose I say x square plus 2y square equal to 1. What are solutions? You have to take y is equal to 0 only, and then x square equal to 1, so x equal to plus minus 1. So if you take plus sign here and d is a positive integer, then there is nothing to be done here. Therefore, one is trying x square minus dy square equal to 1, where d is a positive integer. Okay. Now, this equation was solved in 12th century essentially by Bhaskaracharya by using the development of solutions by the previous mathematicians, and he's putting his own ideas. And in Europe, it was solved much later in the 17th century. Essentially, Fermat had put some questions to. Fermat was a French mathematician, and he put some questions to Europe, the British mathematicians essentially, and we will see that equation soon. But then Brauker gave a solution to that problem. So he was the first European to solve Pale's equation in some sense. And now, why do we solve this, and what is the advantage of solving this equation? So you see, if you look at this equation, x square minus dy square is equal to 1. So if x and y are large, you see that this x square minus dy square is very close to 0. Right? 1, you can replace 1 by 0 here. That is, x square is approximately equal to dy square. Right? Suppose x, y are 5-digit numbers, 7-digit numbers, like that. And then x square equal to dy square. Therefore, root of d is approximately equal to x upon y. So that's how the use of solutions of this equation was done for finding rational approximate values to square root of d. So that is one use. In modern mathematics, you study quadratic uh, numbers, quadratic fields, numbers of the type a plus b root 2 or a plus b root 7, such numbers. These are called as surds or quadratic surds, where a and b are integers or rational numbers. And there you consider a ring which is called as the ring of algebraic integers in a quadratic field, and then you are studying units of such a ring in algebra especially, or number theory. You are studying units of rings, and the units of this ring obtained, q root of d is obtained, the units are obtained by solutions of equations of this type: x square minus dy square equal to 1, or x square minus dy square equal to minus 1. The solutions of these equations give units of the quadratic ring. So that is one modern implication of the solutions of Pale's equation. So if you have small values of d, then it is actually solved easily. This equation can be solved easily. X square minus 2y square equal to 1. So you go on trying. Of course, if you take y equal to 0, then x equal to plus or minus 1. That's the most trivial solution. Then you try y equal to 1. If you take y equal to 1, then x square equal to 3. But x square equal to 3 is not solvable in integers, right? So you go to the next value of y, take y equal to 2. So y equal to 2 gives us x square equal to 2 into 2 into 2 plus 1. That is 8 plus 1. So x square equal to 9 and x equal to, therefore, 3, or you can take minus 3 if you like. So 3 square minus 2 into 2 square is equal to 1. And you get 3, 2 as a solution. And you can also change the sign and you get other solutions. So by trial, when the value of d is small, you can solve this equation by trial also. Unfortunately, when the things become large, the value of d becomes large, this trial idea does not work. Nowadays, we may use computer and the computer which does exact calculations, and then you can, or you should write an algorithm to get exact multiplication and so on, then you can try it using computers. But when Farma asked this question, he asked this question with d equal to 61. X square minus 61 y square equal to 1. Solve this. And then if you try and try, you will not succeed. That was the idea of Farma, unless you have some method of arriving at it. And probably Farma, either he was a lawyer, but he was also a mathematician. He might have got some method to solve it, or because Shah Jahan actually he translated this Lilavati and some texts like that in Persian language. So it went to Europe from there. Maybe he might have read some books and he might have also understood the method, and then he challenged other mathematicians. Is a possibility, we don't know. So in any case, this method was known in the 12th century to Bhaskaracharya, and there are many discoveries which were done by Indian people. But some other countries sometimes claim that we have also done these discoveries, because in different countries there are intelligent people and they think about certain problems independently also. So people claim that we have also done this, like Bhaskaracharya has done problems which are related to remainder. Find a number which leaves remainder 5 when it is divided by 7. And also, remainder is 3 when the number is divided by 15. And also, the remainder is 10 when the number is divided by 23. So, such problems, remainder problems, are there in Bhaskaracharya also. But Chinese people also say, see, we have also have some problems of this type, and so on. However, the important thing about this Pales equation is that no country has claimed that they have solved this equation, Pales equation, or the equation x square minus dy square equal to 1. So that credit of this problem, Pales equation solution, goes to Indian mathematicians only. And there is a interesting history how Indian mathematicians have solved it by using the results of previous mathematicians, like Brahmagupta, who was essentially after Aryabhatta. He was in the 6th century. So Brahmagupta, he solved these equations, uh, x square minus, so we started with solutions of such equations: x square minus dy square equal to plus minus 1 plus minus 2 plus minus 4. If you know some solutions of this such equations, then you can go ahead and solve the main Pales equation, where x square minus dy square equal to 1, you want to solve that. So some methods he had developed, and if d is equal to 92, for example, he has a solution. And many such problems could be solved by the method of uh, Brahmagupta, provided you know, for example, when the right hand side is plus 2 minus 2 plus 4 minus 4, then he can do some manipulations. Okay, so this is d equal to 61 I am mentioning here, and Bhaskaracharya solved this. Actually, d equal to 61 problem or d equal to 67 problem, these are already the problems in the Bijaganita of Bhaskaracharya, and he asks you to solve those problems by using the method that he has given. Okay. So later on in the 18th century, Lagrange gave a solution to Pell's equation, although Blocher was the first, but his solution may not be very systematic. But Lagrange's solution was very interesting, and he gave a continued fraction method to solve this Pell's equation, which we are not going to study. We want to study the method of Brahmagupta and Bhaskaracharya. So Brahmagupta discovered an interesting identity: a square minus nb square into c square minus n d square. You see that these are left hand sides of the equation that we want to consider. Okay, x square minus something into y square. Okay, that is the left hand side. D into y square. D can be 2, 3, 7, whatever. So that n we take some n. X a square minus n b square into c square minus n d square is equal to. Interesting is interesting thing is that the answer can be written in the same form. That is, if you multiply, you will see AC plus NBD square minus n times, n is common, n times AD plus BC bracket square. So it is some square minus the same n into another square. So this is an important identity which is similar to the identity for complex numbers, for example, that if you have z is a complex number a plus ib, then mod z is root of a square plus b square, and mod z square is a square plus b square. Now you multiply these two things and you get again sum of squares. Sum of squares into sum of squares is equal to sum of squares. You get there. Same form you are getting. You may also compare with a plus ib into c plus id, and how you multiply them, and you get some similar expression there. So Brahmagupta discovered this identity. Okay. Actually, Brahmagupta also developed quadratic search, and this study might have helped him to arrive at this identity. Because what we study in the high school, that is a plus b root 2 divided by c plus d root 2. How will you simplify this ratio? Okay, so multiply by the denominator by conjugate, etc. That method we know. So he has studied, Brahmagupta has studied these surds and some properties of surds he had obtained. And therefore, using those properties, he would have seen that such an identity is there. And this identity he tried to use to solve Pale's equation. So let us see what happens here. Suppose a square minus n b square equal to u and c square minus n d square equal to v. Then if you take product, you will get, by using that identity, AC plus NBD square minus n into AD plus BC square equal to UV. So if right hand side is U and right hand side is V in another such equation, then you can get a new equation of the same type in which the right hand side is U times V. Now, you may say U and V are small, then U becomes large. So you are solving an equation in which right hand side is large. But still, this was used by Brahmagupta, and let us see how he used it. So let us see this method of Brahmagupta to solve x square minus 92 y square equal to 1. Now, he first of all gets a trial solution, which is not actual solution. Suppose you take x equal to 10 square, x equal to 10, then x square is 10 square. And now if you take y equal to 1, so x square means 100 here, 92 into 1 square. So that is 92. And the difference of these two quantities is 8, which is small in some sense. Actually, we want the right hand side to be equal to 1. And at present, we have got 8 by this trial method. Usually, you can if you put some x and some y, you get something on the right hand side. And you try to, by guessing, you can get it to be some small number. So Brahmagupta gets this triple 10, 1 and 8. So 10 is x, 1 is y, 8 is the right hand side, and the right hand side you want to make to be 1. Okay, now he composed this triple 10, 1, 8 with itself. Compose means, like you see here, a square minus nb square equal to u and c square minus nd square equal to v. You are composing and getting a new equation in which the right hand side is u into v. Right hand side is u into v. Left hand side is x square minus n y is ad plus bc square. So you compose and get something, some new equation you get. Actually, you want to solve the equation when right hand side is 1. But somehow we try to get more complicated equations, and using them you want to solve the problem. So now you compose it. Compose means 10, 1, 8, 10, 1, 8. You put these things together, and then you have to use this rule. For example, AC plus NBD. N is 92. So AC 10 into 10 means 100 plus N means 92 and B into D means 1 into 1. So 100 plus 92 is 192, that is written over here 192 square. And the second thing is AD plus BC, that you see usually complex numbers calculations, AD plus BC. So what is AD plus BC? 10 into 1 plus 1 into 10, because you are composing with itself. So it is 20. That is y. So 192 square minus 92 into 20 square is equal to, well, you don't have to simplify. The answer is 8 into 8. That is 64. So this is how Brahmagupta's identity is used. And we have got a new equation which looks more complicated. But now the trick is you divide throughout by 64. Now, if you divide by 64, 64 is 8 square. So, you should divide 192 by 8 to get 24. And divide 20 by 8, and unfortunately you get 5 by 2 here. So, if you had got an integer here, you would have solved the problem. But you have got here 5 by 2, which is a rational number. So, it is not the final solution. You have been successful in getting rid of this 64 and getting 1 on the right hand side as required. But the sacrifice that you are making is, instead of integers you are getting fractions. If the problem is unsolved and you want to get an integer here, how will you do that? Again, Brahmagupta's trick is compose this with itself. Now, if you compose with itself means our rule AC plus NBD. So N means 92, AC means 24 into 24, and 22 times 5 by 2 into 5 by 2. Okay. Now this 92 is divisible by 4. Therefore, you are able to get rid of the fraction because you are multiplying by 5 by 2 times. So you are getting rid of fraction, and therefore you are getting 1151 square minus 92 into 120 square is equal to 1, because 1 into 1 is 1. So once you have 1 here, you are getting the same number 1 here. And by this, it is called bhavana also. This composition method, we get the solution to the equation x square minus 92y square is equal to 1. So Brahmagupta solved Pale equations, different Pale equations, by taking various values of n. This is n equal to 92 here, but you can take try n equal to say 60 or whatever. Various values you can try and get the answer. So uh, in many equations, what he did, somehow we reduced the equation to the equation when this right hand side is plus minus 1 plus minus 2 plus minus 4, and after that he used this repeating composing with itself and so on, and then we can get it. But Brahmagupta, although he solved the problem for many values of n, he was unable to solve it for all values of capital N. And that work was done by Bhaskaracharya. But before Bhaskaracharya also, people were trying to solve this problem. As today, uh, Dr. Bedekar madam mentioned that problem of solving number of partitions. How many are there? So that problem was tried by Bhaskaracharya, probably not successfully, but Ramanujan and others, because there is a formula for Euler for partitions, by the way. So that is a recurrence formula, which is very useful. And asymptotic formula was given by Ramanujan. But the idea is that whenever a problem is a challenging problem, people go on try to solve it, the challenge, and then there is some development of mathematics because of these trials. So Jaydev also gave a method, and Bhaskaracharya confirmed this, and he asked many difficult problems like 61, 67, and so on, which were not solved. D equal to 61, 67, they were not done by Brahmagupta, because some modification in this method was required, which was done by the later mathematicians. So taking inputs from Brahmagupta and Jaydev, the first general method for solving the Pale's equation for all n was given by Bhaskaracharya. And he called that as Chakravala, or the cyclic method. So in this method, first of all, you take two relatively prime integers, a and b. Then you consider the triple ABK. This triple means it is a solution to the equation. That means a square minus n into b square is equal to k. Actually, what you do, you take a and b, some values, and substitute there and get some k. But just to uh, make the number of steps less, you try to take values of a and b so that a square is somewhat close to nb square. Okay, a square is close to nb square, so the difference will become somewhat small, and that is the starting point. Otherwise, you can take any a and b and get some k, that is different. But if you choose a square close to nb square, then that will be useful and number of tests will become less. So you should do that. Initial approximation to the problem should be good one, so that your work becomes less. Okay. So now you are having, let us call this as kind of approximate solution, where k is to be later on replaced by 1. That is our requirement. Now we have another triple m1 and m square minus n. Okay, m square minus n. Yeah, m square minus n. You see that This is always a solution because we have just calculated m a equal to m, we put m square minus n times 1 square. So k has to be m square minus n. That's what we have done here. So now this is one more triple that we have got, or another solution I would say of the same equation. Same equation means type, same type. Right hand side is different. Here right hand side is k, here right hand side is m square minus n. And you should try in such a way that m square is close to n. That is good. As far as possible, you should do that. So that this will also be small. Now, if you see in the previous method of Brahmagupta, he has obtained one solution and then composing with itself, he has got a new solution with different right hand side, and then you divide by 64, okay, compose with itself, and ultimately get the solution. So here what we are doing, the difference is you are trying some other auxiliary solution, which is again another, we can say, approximate solution in some sense. That is, the right hand side is not 1, but it is some different number which can be made small because m is at your disposal. So suppose I take n equal to 13, then I can take m equal to 4. 4 square minus 13 would become uh, for 16 minus 13, that is 4. So maybe it is a small number, and if it is 4, you can even go to Brahmagupta and use his method and solve it. That is one possibility. But if it is not, then you have to continue with this method of Bhaskaracharya. So Bhaskaracharya, what it does, first of all, you take one triple, then another triple in which b is equal to 1. Now compose this. This composing is the idea of Brahmagupta. He has the identity and use that identity and get the new triple. New triple is am plus nb, comma, a plus bm, that is x equal to the first number, y equal to second number, and k into m square minus n, that is the third number, which is the right hand side. So you have got this equation am plus nb square minus n times a plus bm square is equal to k into n square minus n. And remember, this right hand side you want to make as 1. Okay. Now you are dividing by k square. Now it may surprise you that in the method of Brahmagupta, in this example, this 64 was a square. It was 8 square. And you are dividing by 8 square. So 192 is divided by 8 and 20 was divided by 8. So that becomes 5 by 2 rational number. It's okay. Then you modify it, etc. But here you are not getting k square on the right hand side. Okay. Even then, we are dividing by k square. So you are directly allowing rational numbers in this. So divide by k square to get the triple am plus nb divided by k, a plus bm divided by k, m square minus n divided by k, and it satisfies m plus nb upon k square minus n times this y square. Y is a plus bm upon k, a plus bm upon k, and right hand side is m square minus n by k. Now the idea is that you should see this m, and m is actually arbitrary, it is at your disposal. So you should choose m in such a way that m square minus n is divisible by k so that it will become an integer. That's the idea. Not only that, you also require am plus nb upon k as an integer and a plus bm upon k as an integer. So we want these three numbers which are looking like rational numbers as integers by a proper choice of m, because m is at our disposal, and you should make a proper choice of m so that these three numbers will become integers. Now, how to choose this m? For that, you are using Kuttaka method or linear Diophantine equations solutions. You can do it in modern way or using Kuttaka method. You can solve it. You see that a plus bm, this a plus bm uh, is divisible by k, right? That means bm plus a, last time you have seen that, is equal to k times y, okay? K times something. So that is a Kuttaka equation. And we can find the value of m there. M is the Kuttaka or something to be found out. And you can do it by trial also. But if the numbers are large, then to solve it, you use Kuttaka method. Okay, so the use of Kuttaka method is also there in the solution of Pale's equation, especially when the value, these are more difficult problems. That is, the values of n are large, like even 61, 67. These also are challenging problems, as you will see. So, basic solution to this is B is actually invertible modulo K. Why? Because you see that A and B are coprime, that we are given. Because A and B are coprime, B and K are also coprime. Because if there is something common with B and K here, you will see that that common thing will divide A also. And that would mean that A and B GCD is not 1. So this means B and K, they are coprime. And once B and K are coprime, you can solve. And B is invertible modulo K. And 1 by me, I have done with some reason. It is actually A B dash, where B dash is the inverse of B modulo K. Last time we have seen inverse. So it is actually minus A B dash, which we can write in the form A upon B modulo K. All right. So if M is minus A upon B, you should choose that. And see, this M is unique modulo K. Okay, there is a value between 0 and K minus 1, which is taken by M. But the answer is unique mod K. That means if you add K to it, or add 2K to it, or add 3K to it, or subtract, then also that is a solution. So now let us look at m square minus n. You see, not only we want that a plus bm is divisible by k, which we have achieved by taking m is congruent to minus a b dash, where b dash is inverse of b mod k. But what about m square minus n by k? Is m square minus n divisible by k? Let us see that. It automatically happens that m square minus n is divisible by k. So m square minus n is congruent to a square upon b square minus n, where b dash actually it works, although we are writing in the rational form. So a square upon b square minus n, which is congruent to a square minus n b square upon a square. But you see, what is a square minus n b square? See, a square minus n b square we have taken at the beginning. A, B, K, that is a triplet. That means a square minus nb square is exactly k. That means it is divisible by k, and a square minus nb square is actually divisible by k, and that is 0 mod k, because numerator is divisible by k, so it is 0 mod k. That means not only this m square minus n is congruent to 0 mod k. M square minus n is congruent to 0 mod k. So the problem of this is solved. M square minus n is divisible by k. That is what we have proved. Okay. Now, if this is an integer and this is also an integer, therefore this square is an integer. Okay. And this is a rational number, probably. But if the rational number is its square is an integer, then that rational number is also an integer. Please check that. If square of a rational number is an integer, then that rational number is also an integer. So by choosing this a plus bm properly, we can get that m square minus n is an integer and this is an integer. All right, so far so good. We have got a solution here in integers for this pale type equation. Not actually right hand side is now may not be 1. If it is 1, it is a great thing, you are through. So it is pale type equation and we have got integral solution. Okay, now what you do, you minimize this m square minus n by k. That means there are many values of m. You try various values of m and choose the one for which m square minus n is actually minimum, divisible by k, and it is minimum. And also see to it that all these numbers are also integers. So that minimum value is important because ultimately you want to reach 1. You want to reach 1 on the right hand side. So we try to minimize m square minus n by k. So once we choose m so that a plus bm by k is an integer, automatically also are the other two numbers in that triple. Once one m is obtained, adding or subtracting multiples of k, we get all such m. Among such m, choose one that minimizes m square minus n by k. Okay, one that minimizes m square minus n by k, and repeat the process. This method always terminates with a solution. Actually, it is not clear that why this process terminates, but it is proved by Lagrange and also proved by many other people. Different people have proved it that this works always. Bhaskaracharya has not given any proof that it works, but he stresses, essentially he says that it works. So sometimes there are different proofs of a theorem. One of the proofs is proved by intimidation, that you say it works, so it works. That's all. So no proof is given by Bhaskaracharya, but others have proved that the method of Bhaskaracharya works. And so we believe that certainly now, because already proofs are there of the method of Bhaskaracharya, and for any n it will work. So this process terminates, and for n equal to 61, see the smallest solution. Why Verma gave this problem? You cannot do it by trial because smallest solution is x equal to 1766, 319049, and y equal to 226153 is 980. So it could not be solved by trial unless you have some method with you You cannot solve it. So that's why Brahma gave this 61. Actually, he might also know 67, but 67 gives a smaller solution. And both the problems were asked by Bhaskaracharya in his verses in Bijaganita. So just to illustrate, let us do one more problem. One we had done, which was solved by Brahmagupta when n is 92. That was solved. Now we do this problem posed by Bhaskaracharya, x square minus 67 y square equal to 1. So what we do here, a square minus 67 b square equal to k. You try some solution, and what are the possible values of a and k? You see that this 67 is close to 8 square. 8 square is 64. So you take a equal to 8. So 8 square minus 67 into 1 square is equal to k. That k is minus 3. So this is the starting approximate solution, as you can call it. Now find m so that a plus bm, that means 8 plus m, right? A is 8 and b is 1. So this is 8 plus m. You want to find m so that this is divisible by 3. Fortunately, divisible by minus 3 means divisible by 3. So what are the values of m? I can take, of course, m equal to 1. So 9 is divisible by 3. Now, if you add 3, that's okay. 4. 8 plus 4 is 12, divisible by 3. Then add 3. Because the solution is unique mod 3, as we know. So 1, 4, 7, 10, etc. are there. Out of them, choose m so that m square minus n is minimum. So here n is 67. N is 67. So what is m? You can take m to be 7, because 7 square is 49 and 8 square is 8 square also it could be, but 8 is already there, right? Because you had solution. If I put m equal to 8, then 8 square 64 minus 67 is minus 3. So you could get a solution with minus 3, which is already there. So instead of that solution, we take m equal to 7. All right. Now we get the triple m plus nb upon k square minus n into a plus bm by k square is equal to n square minus n by k. Substitute there, a is 8, m is 7, etc. and you simplify. Then you will see that 123 upon 3, 15 by 3, 18 by 3 is equal to 41. So that is 5, 41, 5 and 6. Okay. 18 by 3 means 6, like that. So this is the triple. This is the triple means 41 square minus 67 into this 5 square is equal to 6. And check that 41 square is 1681, 67 into 5 square is 1675. So answer is 6. Okay. So this is another thing that we have done. Now you have to compose these two solutions, 8, 1 minus 3 and 41, 5, 6. You should compose. What do you get? You know the formula of Brahmagupta. So you compose in the same way. We have done one composition earlier. So similarly, A into C, etc. 8 into 41, that is here, plus 67 into 1 into 5, 1 into 5, and so on. You can do that by that formula, which is given here, AC plus NBD and AD plus BC. AD plus BC means 8 into 5 plus 1 into 41, means 40 plus 41, that is 81. And minus 3 into 6 is minus 18. So our triplet is 663, 81 and minus 18. Now you can divide by 9, and you get, of course, divide this by 9 means divide 663 by 3 and divide 80, this 81 by 3. So 221 square minus 67 into 27 square is equal to minus 2. Now you get minus 2 here. Then you are in the land of Brahmagupta. So you compose with itself. Once you compose with itself, by that same Brahmagupta's formula, you get this triple 221 square plus 67 into 27 square. See, itself means squares are coming there itself, therefore. And now this is 11934, comma 2 into minus 2 is 4. So 97684, comma 11934, comma 4. Now divide by 4. That means the first two terms you should divide by 2, isn't it? Because square of this minus 67 into square of this is equal to 4. Divide by 4, that means divide first term by 2, second by 2, and third by 4. That gives you the answer 488415967, and so we get the required solution. 48842 square minus 67 into 5967 square is equal to 1. And so it cannot be done by trial, you see. Although computer can try it, but not we. So therefore this method is important. Moreover, as I have told you, 67 is the value of n here, and root of capital N means root of 67. You can find what is the approximate rational value of root 67. So 67 is equal to approximately this square upon this square. Therefore, root of 67 is approximately 48842 divided by 5967, because 1 is replaced by 0, because these are large numbers. So this is how you can get approximate rational value of root 67. Also, as I mentioned, units in the ring in Q root 67 you can obtain, namely this 48842 plus 5967 into root of 67, that is a unit in that ring. So this is another. So okay, so I will stop here. If you have any questions, most welcome. So I have explained here Brahmagupta's method and also Bhaskaracharya's method, and this Pell's equation, how it is useful, that I have explained into different ways. Yeah. So if you have any doubts or queries, or if you want to make any comments, you are most welcome for this thing.
Yes, any comments or questions from the audience? If you have any question or doubt in your mind, you can ask. Uh, don't
Yeah.
hesitate. If you want, you can ask.
Yeah. So I think it's a difficult problem, very difficult problem, and even Indian mathematicians took a lot of time to solve it.
Yeah.
Means here you see that Brahmagupta was in the 6th century, 7th century, and then Bhaskaracharya was in 12th century. So they were concentrating on other problems, astronomy also especially. And this was an interesting problem which was difficult to solve. Some people paid attention to it, some people did not pay attention to this problem. But Jaydev and Bhaskaracharya ultimately gave a very nice solution by using the composition of Brahmagupta. Yeah. And Brahmagupta actually was called, highly praised by Bhaskaracharya. Brahmagupta, although he made some wrong statements also. Like, Aryabhatta essentially said that the earth is moving around the sun, but somehow Brahmagupta did not believe that. He said Aryabhatta is wrong. He was saying that sun is moving around the earth like that. So he had some misconceptions also, but he corrected some results of Aryabhatta. For example, Aryabhatta tried to give formulae for volumes of solids, and his formulae, some of them were wrong. Actually, his formula for area of a circle was correct, pi r square as we write it nowadays, and circumference of a circle, but volume of a sphere, his formula was not correct, and volume of a tetrahedron, for example, or volume of a pyramid. So he actually tetrahedron means one third base into height. That is the formula. But Aryabhatta gave one half base into height, which is wrong. Probably Aryabhatta might have taken average of base and top. Top is zero actually, because there is a point only at the top. So he might have taken average of that point and the base. And so he gave the value as one half of base into height. However, uh, it was Brahmagupta, he corrected that formula and he wrote one third base into height. So that's how mathematics went on improving by experiments and more and more thoughts in India. And even the formula for volume of a sphere was not corrected by Brahmagupta. But only Sridharacharya has a formula which has a hint to the correct formula. But the correct formula was given by Bhaskaracharya, 4/3 pi r cube. And in fact, the method of Bhaskaracharya is that of calculus. Well, what he did, he wrote that sphere as a union of pyramids, starting starting from the center. You take a pyramid which starts from the center, and or tetrahedron kind of thing, and its base is on the surface of the sphere, and the sum of all these volumes of these pyramids is the volume of the sphere. So in India, Bhaskaracharya was the first one to give a correct formula with its proof for the volume of a sphere. Of course, we know Archimedes was the first to give this formula, and he gave a correct formula 4/3 pi r cube. Was considered one of the greatest mathematicians of all time, Archimedes. But in India, Bhaskaracharya was the first one to give the correct formula, and the method of Bhaskaracharya is different from that of uh, Archimedes. Yeah. Okay. Any question? Any other question is there? Then we will discuss that.
Okay, so it seems there are no questions.
Okay.
So thank you, sir, for introducing us to the mathematics of Bhaskaracharya and Brahmagupta, and hope participants will be encouraged and they will look forward to study this material. And so we will have a lunch break now, and we will meet in the third lecture of today, and that will be again delivered by Professor Khatri. So we will meet at 2:30 p.m. So please join well before time so that we can start on time.
Okay. Thank you.
Okay, sir. Thank you.